soaked in folds of midnight waters, side by side, we sons and daughters. We set forth for no king's orders, but we'll sail together. Hold fast, tides are turning, flames roar, fires are burning, we'll all be returning if we sail together.
So last night I presented the Riemann-Ziegler, which is a shortcut and approximation that shows the oscillation at certain intervals that tries to guide the user into which interval that possibly will have the non-trivial zeros of the zeta function. Prior to that, I did spend all day just trying to understand the Riemann function, and it turns out that I got really confused, and I was actually combining two equations that and that I realized that the two equations, the first one, the infinite sum, which is actually from Euler's, is actually quite different from Riemann. I got confused because it's considered to be a simple zeta function, although Euler actually, that wasn't the intention of Euler. And in fact, he proved the basal function, the pi squared over 4, was it pi, or over 6. Pi squared over 6 is the infinite sum when the power notation is 2. So it's actually, that was the basis for Riemann. But Riemann is the one who really, who's really trying to solve the zeta function. So, and then he made it into a complex function. So it's his equation then becomes S equals the sigma plus IT, the imaginary. So I didn't know that. So right now, so this presentation is about showing the infinite sum series with the S in the 1 over n to the S infinite series sum. As you increase the power notation, you see just how fast it will converge when s is greater than 1, how fast it will converge to almost nothing. The zeros keep getting bigger by s is equals 100,000. That's about over 30,000 zeros. So that's what it is. And you might think, well, where's the 1? Because the y output, it will always be 1 plus some kind of residue. The highest residue is when s is equals to 2, and that is what Euler proved, the 1.6449. That's the number, and that's the highest output for the infinite sum. After that, it just keeps going. It's lower and lower until it's close to 1. It's close to 1 for s. S should always be 4, and that's something that we can see, that behavior when s has to be greater than 1. Okay, so it will converge to almost 1. And the output is 1 because the first term, which is the 1, and n is always going to be 1. 1 divided by 1 divisor, and whatever s is, that, the first term will always create an output of 1, a sum of 1. And then it's just that when you increase the s, you're just increasing by how much or how little. So when s is like 100,000, you're really just adding like a very, very tiny dust, very microscopic or myopic amount, or so very, very tiny amount. So that's what it is. It's always going to be a negative slope. And while I'm only showing the leading numbers, non-zero numbers, it's actually supposed to be 1 plus that residue. So I just did that because so that it can be more flexible. We can show it better. So I'm using digits instead of the actual real number value, not a scientific notation. I think it's just much easier for the y-axis to be the number of digits, and then if there is a kind of dynamic leading digit, then also include that. But ChatGPT only knows up to 37, s equals 37. After that, it's all 1, and it is really like that. Like, it's really so many zeros, 1, and even so many zeros after that. Then there could be just a few more non-zero digits, but that's it. It's very, very tiny. And what else? The number of digits. How is that calculated? Well, after the 52nd s, you kind of just estimate it. So whatever s you have, you just multiplied it by 0.301003, I think. So that's kind of, so this is the visualization of Euler's infinite sum series.